Welcome everyone. My name is Enrique. I'm a lecturer here at the University of Auckland, and I am part of the ASG committee. My work is related to FRP and concrete, not really to steel, but we have the expert in the room. Before I introduce Lydell, a couple of housekeeping items. First, if there is an emergency, fire, earthquake, we just go through the main door and in front of the building. Toilets are just there on the right-hand side. Please put your phone in mute or switch it off so we don't have awkward situations. And make sure we are changing our mailing system. This is mostly for the people that are going to watch this on YouTube, because if you are here, you are probably in the new mailing system. If you are not, remember to go to the ASG, the Auckland Structural Group website, and join the new mailing system. We had to change because of problems with the law and how we keep the data and all of that. Finally, let's get into today's presentation. We have here Lydell Wiebe, who is an associate professor at McMaster University in Hamilton, Canada. Not Hamilton, just the south, a little bit farther. He is doing a sabbatical in Canterbury, University of Canterbury in Christchurch for 6 months. And today he's going to talk about how to design for reoccupancy with control rocking braced steel frames. Please join me in welcoming Lydell.
Thanks very much, Thanks, Enrique. I'm just going to check first that the mic is working, and I think I hear a little bit of myself, so I'm guessing that it is. It's great to see so many people here, some familiar faces and lots of fresh faces as well. So thank you very much for taking the time out of your evening to come. Again, my name is Lydell Wiebe. I'm from McMaster University in Hamilton. I'll talk about design for reoccupancy with controlled rocking braced frames. I'll talk a little bit at the end about some other projects that we've been doing recently, kind of in the same vein, but not with controlled rocking braced frames. But before, at the beginning, I thought I'd say a few words about where I'm coming from, McMaster. So it is Hamilton. We're slightly closer to Toronto than Hamilton here is to Auckland. So we're about an hour from everywhere. We're an hour from Toronto, an hour from Buffalo, and an hour from Niagara Falls. So that's where I come from. But to put it in terms that we as structural engineers might understand better, here's where I come from in terms of design spectra. At the bottom here is Hamilton. So that's in the pink here. The blue dashed line is where you are in Auckland. So at most periods, except at very short periods, I have a fraction of the spectrum that you have. So I get to study earthquakes from a safe distance. You might think that you have low seismicity in Auckland, but we actually have quite low seismic hazard, which is nice. If I look at Wellington, here is in blue, Vancouver is in the pinkish color. Those spectra are pretty close to each other, but keep in mind that in Canada we designed for a 2,500-year earthquake. In New Zealand you're designing for 500 years. So the spectrum might be similar, but the hazard in Wellington would be significantly higher than in Vancouver, which is still our highest seismic risk in Canada, not necessarily highest hazard, but highest risk. And then Los Angeles here blows everything else out of the water, which is why we often use California as our test bed for checking out some of these systems and seeing how they perform. So some of the examples I'll give you are designed for California largely for that reason. In terms of McMaster University, our laboratory is not to the scale of what you have here, but there's a lot we can do. We have 3 shake tables, a series of actuators, a pretty impressive looking shock tube, and a series of things we can do. So I'll show you some tests that we've been doing at McMaster, and also some work that I did during my PhD at École Polytechnique in Montreal. We have quite an active earthquake engineering research group at McMaster as well. So these are some of my colleagues and myself in various aspects of earthquake engineering. So despite being far from where the source hazard is, there's a tradition of earthquake engineering at McMaster that we continue to maintain. So with that background, my plan for the talk today is to talk first about seismic performance and what we expect if the structures are behaving as we as structural engineers might anticipate, and how we might want them to behave. And I think that many of us in this room are probably already sold on the idea that there seems to be a disconnect between what structural engineers expect and what the public is likely to expect. And then I'll talk about controlled rocking braced frames in the way that you would deal with them as a designer, which would be first to look at the design of the base rocking joint, then the capacity design of the frame, and then the connections to the floors, and I'll go through each of those in more detail on the first two than the third. I'll talk about non-structural components in these systems, which I think is something we need to think about if we're looking at losses and seismic performance, and finally some other research within that general umbrella of how we might design for more rapid functional recovery. So first off, what do we expect? What do we want? I'm sure all of you are probably more familiar than I am and have seen this presented in various ways, but what happened in Christchurch 9 years ago now. The blue dots are all buildings that were slated for demolition, and as we're quite aware, there were a lot of buildings that ended up being demolished for a variety of reasons, one of which would be the structural performance. When I asked structural engineers what surprised them the most about the Christchurch earthquakes, the most common answer that I get is, I was surprised by how well the structures performed. Given what a big earthquake it was, I would have thought that we would have more significant life safety concerns with some of the buildings. From a structural engineering perspective, it seems that things are working fairly well in terms of life safety at least. And yet I think we're fairly well agreed that the public has not shared that view. And so, yeah, looking at how we can rectify that disconnect. I think of it in terms of a metaphor of our seismic design as being like a crumple zone for our car, which I think it even looks like a lot of what we do in structural design, as I'll show you. We design a crumple zone that will absorb the energy of the impact, and we'll design things to keep the occupant safe. I think there's a couple of key differences, though, between designing a car and designing a building. One of them is that we do not expect that every car on the road is going to get in a major head-on collision at the same time. But we do expect that all the buildings in a major urban area are likely to see quite similar levels of shaking, at least within a confined zone. Second piece is that a car is mobile. And so if you need to replace the car, you can bring one in from somewhere else, relatively easy, and be back on the road. A building is constrained to a piece of property, and so the time that it takes to figure out what to do with the building and then to repair or demolish or whatever, this, as we've seen, can take years. And then there's all sorts of other factors that come into play with cordons and insurance and all of these sorts of things. But in short, it's taking a long time, much longer than it would take for a car. And our seismic design in steel can look like this. Here's a steel plate shear wall. It looks like a lot like a crumple zone if it does what it's supposed to do. Here's a braced frame. Again, we have buckling of the braces. We've seen in Christchurch that there are ways of fixing things, more EBFs than CBFs there. But it can be possible to fix, but still we're relying on the damage there to provide the life safety. And so the philosophy motivating most of my research is, can we shift our metaphor? Instead of thinking like a crumple zone for a car, can we think like circuit breakers in our home? Which also have lots of parallels. We're protecting the more vulnerable elements within the system by having something where we understand the capacity really well. But here is something where we can return it to surface much more rapidly. And so that's the thinking that's motivating lots of what I'll be presenting today. Rocking would be one system that would fit under that umbrella of trying to return the systems to occupancy more rapidly. So we're a concentrically braced frame. We're relying on yielding and buckling of key structural elements, and we'll design to avoid fracture of those elements. We'll capacity design to ensure that the connections can develop the strength of the braces. In a rocking system, we're going to intentionally allow some limited uplift from the foundation. We will control it using a combination of post-tensioning and energy dissipation, and in that way we can have the nonlinear response that we want. It limits our seismic forces without the damage that tends to be associated with that. In terms of the mechanics of the system, which I think are important for understanding how it works overall, it's actually fairly simple and intuitive to understand. If I think of a frame and it's post-tensioned down, when I start applying lateral force to the system, it has that high stiffness of a braced frame. So until it starts rocking, it doesn't know that it's a rocking system. Until you overcome the pre-compression at the base, it's like any other braced frame. And then you reach the point of incipient rocking where you have overcome that pre-compression. It's easy to calculate where this is. Just draw a free body diagram of the system. And then beyond that, as the system rocks, it's going to elongate the post-tensioning, and that provides a restoring stiffness to pull the system back towards zero deformation. If we unload and we go back the other direction, we have this bilinear elastic response, and when we take the load off, it's self-centering, so the displacement is zero whenever the force is zero. And then typically we'll provide some form of supplemental energy dissipation to help control this response. And there are lots of things this can look like. I'll show you some examples a little bit later. But essentially we're going to enclose some area in the hysteretic loop so that relative to a more, to a full elastoplastic system, we have less energy enclosed in a loop, but we do have the advantage of, if we unload from the peak displacement, instead of having this locked-in residual displacement, we always come back through zero displacement at the end. And so that's what we're trying to achieve with these self-centering systems. In terms of what this can look like, I thought I'd start off with a video of an example of one of these. This is shake table testing that I did in my PhD, so this is back in 2011 now. It was a 30% scale model of an 8-story frame, so about 9 meters tall, fairly representative of things, and we did this at École Polytechnique. And so on the left here is the frame. In yellow is the frame we're actually testing. The red is all lateral supports and work platforms. To give you a sense of scale, this is me working on it. And this will be a video of what it looks like in the biggest earthquake that we ran on it. You'll have seen quite a bit of motion. Again, that was a really big earthquake. You'll have seen the uplift at the base. You might have noticed these devices, which are friction devices. That's not the only way to build the system, but it's what we did for the lab. You'll have noticed the noise, which is coming mostly from the friction devices and from the hydraulic actuator. We ran my favorite test that we ran on the system, where we disconnected the energy dissipation, and we just did a boom with the shake table and excited free vibration. And when we did that, people would walk by in the lab and not notice that we were testing to 2% drift. It was so quiet as it rocked back and forth, which surprised me. I thought it was going to be really loud. I should mention SCED has a design guide that I was involved in writing a number of years ago for the system, and it's available, published back in 2015. I think overall the framework that we set up there is consistent with what I'll talk about today, although I'm not going to go step by step through it here. There are a couple of details in there where we didn't know the answers yet, and so we put something down, and I think the research over the last few years has developed the understanding there, so there are a few pieces that I would tweak if I were doing it now, but conceptually, I still think it's a reasonable resource to refer to. So I'll point you in that direction. So that's an overview of the performance that we would expect, where we're getting life safety fairly well, but we're not necessarily getting the return to occupancy, and that rocking provides one possibility at least to look at having a less damaged structural system at least, and hopefully moving towards occupancy. So if we're thinking then about how to design it, the first step that you would use as a designer is to design what I call the base rocking joint. So essentially, what's controlling that rocking motion? What's crossing the rocking joint? And there are three components to this. There's the cell or the weight that's acting on the system, shown there. There's the energy dissipation, which controls how big this flag and the flag-shaped hysteresis is. And there's the post-tensioning. So I'll talk about each of those three pieces. First off, for the weight, the key question you have to ask as a designer is whether you're going to use a decoupled system or a coupled system, is how I talk about it at least. A coupled is a system where the frame is carrying the tributary gravity loads for the system. So in that case, the weight will be a significant factor in resisting uplift of the frame. You can maybe use some conventional detailing to the floor systems. On the other hand, if you're using conventional detailing, the slab has to lift up along with the frame. And so you might have some damage to the floor slab, at least if you're not thinking about it. There's also the potential for problems due to impact, where if you have a large mass uplifting, as it comes back down, there's a significant impact force there. Then there's also decoupled. So in this case, we're setting the frame in some way separate from the gravity framing system. So its only job is to carry lateral loads. In that case, we don't really have much weight to resist the rocking. We just have post-tensioning and energy dissipation. And we need some kind of specialized detailing that can transfer those loads. But we avoid the problems of floor damage because we're not lifting the floors up, and we're not expecting major impact problems. So most of the research that I'll talk about here, actually some of the first stuff on the design of the base rocking joint is kind of independent of which of these it is. But most of the experimental results we have are from these decoupled systems, because analytically they're easier to deal with. And 7 years ago, when I was working on the writing of the SCED guide, we included both in there, but my feeling would have been, this is the way to go because I'm worried about impact problems here, and I don't think they're being fully taken into account. At this point, I'm shifting on that. I think that this is going to be, I'm quite sure this is easier to build, and I think we can probably deal with these issues without too much effort. So while I'm not sure we're all the way there, I feel like there's a lot of promise in this direction. But both are available at this point. So that would be the weight component, and it's shown very small here because I'm thinking about a decoupled system. Next would be the design of the energy dissipation. So if you know how big you want this flag to be, and I'll come back to how you might know that in a moment, then you can design some form of supplemental energy dissipation to provide this component of your resistance to rocking. And that can take lots of different forms. Buckling restrained braces have been used. This is from the HP Foundation in California. There have been lead extrusion dampers used at Forte Health in Christchurch, yielding plates in various configurations, friction devices, more from a lab perspective than in practice from what I've seen, but conceptually there's no reason you couldn't use it. Ring springs have also been used. For those of you who aren't familiar, the idea of a ring spring is you have a stack of rings. Some are smaller, some are bigger. When you try to compress the stack, the inner springs have to get a little smaller, the outer springs have to get a little bit bigger, and so that's providing some stiffness, and there's friction between the springs, and so that also provides some energy dissipation. So you kind of get stiffness and energy dissipation in the same device, which has been used in a few cases. So that would be your energy dissipation. Conceptually, you could use viscous dampers. There's lots of things you could use. But you need some way, or you will often elect to provide some form of energy dissipation. And then from a design perspective, if you know what you want your rocking moment to be, once you've defined what the contribution from weight is, once you've designed your energy dissipation, you'll make up the difference with post-tensioning. And that post-tensioning can take the form of strands, like they used in Orinda City offices near San Francisco. It can take the form of bars, but the function of it is to provide a clamping force to resist uplift and also to provide stiffness while rocking. If you don't have that in there, you only have P-delta effects, which is a negative stiffness while it's rocking, which is not necessarily unstable. There's lots of columns that have been standing in Greece for thousands of years without post-tensioning their rocking systems, but generally people, including me, will feel more comfortable having a positive stiffness in that secondary range. You can also get that stiffness from these ring springs. So those will be the three components that you're thinking about for design, but this all presumes that you know how big you want the flag to be and what you want your rocking moment to be. And those are things that you have quite a lot of control over as a designer. It's not implicit in the system like it is for pretty much all of our codified systems. You can control the amount of energy dissipation separately from choosing the system. You control this rocking moment pretty easily. And so what does that rocking moment need to be? How much energy dissipation do you need? From my perspective, the answer to those questions is really how large of a displacement are you prepared to accept? Because those things have a large influence on the displacement. It's not tied to ductility per se in the same way that we think about. So we tend to think of most systems as having a predefined ductility, and that controls what the strength needs to be. In this case, I think of it more like isolation, where you have a deformation capacity, and you can control, ductility is that capacity normalized by a yield drift, but you have very independent control over that yield drift. Strength and stiffness are pretty much independent for this kind of system, and therefore I find it less helpful to think in terms of ductility and more helpful to think in terms of displacement capacity, which means that as a designer, you need to be able to estimate what the displacements are on the system. So what we've looked at over the last few years is millions of studies of SDOF, SDOF systems with flag-shaped hystereses, and looking at how much do they displace relative to a linear elastic system. So essentially, checking the equal displacement assumption for flag-shaped hystereses and then calibrating a correction factor to it. We find in general it does displace more. The question is how much more. So if we look at a flag-shaped hysteresis, what I'm showing here, on the y-axis is the correction factor to the equal displacement assumption. So a value of 1 means equal displacement assumption is right. On the x-axis is the initial period, and then the three different lines are for different values of R, so something like your structural ductility factor, we call it R in North America. Essentially, R of 2 means that you're reducing your elastic design forces by a factor of 2. So if we have R of 2, so a system that's fairly close to linear elastic, and if our period is not short, then equal displacement assumption works well if we also have the maximum possible energy dissipation while staying self-centering. So that's a lot of ifs, but we can get something like the equal displacement assumption there. If we start increasing the value of R, so having the system rock more easily, then our displacements go up. R of 8 is the largest value in the US code. R of 30 sounds crazy because nothing is anywhere close to there. But again, I'm not thinking in terms of ductility. I'm thinking more in terms of displacement capacity. So it's not necessarily unstable when you do that. It just has bigger displacements. If you're prepared to accept those displacements, it's maybe OK. So those would be those factors. And then if we look at having less energy dissipation, so this would be the extreme where you provide no supplemental energy dissipation, then your equal displacement assumption becomes less accurate. You need a bigger correction on it. But again, if you're prepared to accept those displacements, then you might not necessarily need energy dissipation in the system, as long as you are OK with those displacements. We also looked at the influence of this secondary stiffness and found that it had the least influence of any of the parameters within a fairly reasonable range. If it's very high, so you're close to linear elastic with just a bit of softening, then it matters. If it's negative, in some cases, then it matters. But if it's fairly close to flat after the system is rocking, it's not terribly significant, which is why I've tended to quantify things this way as a correction to the equal displacement assumption, rather than using direct displacement-based design, which is all based on a secant stiffness, which implies that this stiffness matters a lot. So we came up with a regression. This is the form of it, and we find it provides a reasonable estimate of the displacements for a self-centering system, at least for the cases we've looked at. And I'd be very happy, there's people in the room who are looking at self-centering systems. I'd be really happy if you tried it out and found out if it worked for your systems. Looking at what this means for collapse fragility, we've looked at questions like, where do you want your post-tensioning? So if you have a given rocking moment, if you put your PT at the edges, then it's stiffer while it rocks because you've got a lot larger lever arm to that post-tensioning. If you put it in the middle, then it's more flexible while it rocks, but it also has a larger displacement capacity because you have less strain on the post-tensioning. So we looked at the interplay between those and trying to see where we would want it to be. And what we're finding, based on some modeling, I should mention actually it's fairly simple to model. It might feel complicated because you're not used to modeling it, but unlike most of our conventional systems, where you have to calibrate some sort of a material model. In this case, we're relying on gaps opening, which is fairly easy to, as long as you can get it to converge, it's not that hard to calibrate it. Getting it to converge is not necessarily as hard as it might sound. In terms of collapse fragility, so this is showing on the x-axis how big the earthquake is. 1 is an MCE level event for California, and we went out to huge values because we could. And looking at the probability of collapse, what we find is having it in the middle is generally better than having it at the edges. So you have lower probability of collapse. You would rather have that displacement capacity, even though you have slightly larger displacements. Using R of 30 is a larger collapse fragility, so it's more likely to overturn than if you use a larger rocking moment. But regardless, we're still falling under the 10% probability of collapse in MCE that FEMA P695 determines. So even a very aggressive value of the rocking moment can still provide enough stability as far as our analyses can tell. One last note on the design of the base rocking joint. I've been talking about moments, but you also need to get the shear into the foundation somehow. So sometimes that's done with a bumper. Here I've shown from my lab tests, but this is also what they did in Forte Health. I've seen it also done with a shear key at the base. So those are some options there. So that would be the design of the base rocking joint for essentially to control the displacements and selecting the post-tensioning and the energy dissipation to do that. The next piece is after you have designed that base rocking joint, how do you design everything else in the frame? What are the loads on those members of the frame? And this kind of boils down, this is maybe oversimplified, to a question of how, it is a question of how heavy does the frame need to be. This is the Forte Health building. This is 141 Cambridge Terrace. They're a few blocks away from each other in the CBD of Christchurch. And you see quite a stark difference in the amount of steel that went into the two. There are lots of factors that play into that, and I understand that the client was still quite satisfied with this. But if you're thinking in terms of the economy of the system, something like this sure looks more appealing than something like this. And one of the factors that can come into play into this is higher mode effects. So this is familiar to those of you who have looked a lot at reinforced concrete shear walls. Here's a moment envelope. This is a shear envelope and over the height of a building. And this is an experimental incremental dynamic analysis. So the video I showed you earlier is the largest black line. This is what we found for the moments and the shears in the system. The other black lines are the same earthquake at different scaling factors. And in red is what you would expect the moments and shears to be if we had pushed on the system until we fractured the post-tensioning. And what we see is we got nowhere close to fracturing the post-tensioning in terms of that base rocking joint, but the moments above the base were quite a bit larger than what you might expect from a pushover. And your base shears could be more than twice what you would expect from a pushover. So this is fighting against capacity design, where we're trying to cut off the forces by having a well-designed fuse. We're finding that the moments and the shears are continuing to increase from there. The way I think of this is in terms of the higher in terms of as it rocks, it's like you're going from a fixed-based system, shown in black, to a pin-based system, shown in red. You're removing the rotational restraint at the base. And if you do that, you can compute the mode shapes for a pin-based structure, even though it's unstable. Mode 1 is the unstable mode. Mode 2 has a longer period, but generally has a fairly similar shape in terms of displacement, or forces, shears, and moments. Mode 3 gets even closer, and so on. So you can think of it in terms of the combination of these modes. And then we turn this into a design approach as well. So we look at, for one of these frames, if we're modeling what's happening while it's rocking, if we have a design spectrum, what we can do is take a model that you'd have in SAP or ETABS and model it like this. So you keep one of the pins at the base, the other one you take away, you show the energy dissipation that's on there, you apply your pushover forces, you apply the post-tensioning to whatever you're expecting to be the displacement or the maximum capacity, however you want to do it, and then you add the higher mode effects computed from a response spectrum analysis as done within ETABS. So it's something that you can do within a computational program that you're using anyway. The other approach that we've looked at for this is to simplify things, because here you have to play with your boundary conditions, which is a bit of a pain if you're changing your design back and forth. So we look at an equivalent static approach where we kind of simplify what we expect those forces to be. And then to validate it, we look at, here's a set of 80 records. This is the target spectrum. Blue is the median of those 80 records. And we looked for this example at a 12-story frame. The blue is the median. The red is what we get from modeling with the changed boundary conditions. And you see we can capture the column compressions, which look a lot like a moment envelope, and the brace compressions, which look a lot like a shear force envelope, by using this approach. If we use the equivalent static forces, we also come up with something that's really seems quite accurate, and it's not an empirically calibrated approach. It's all based on theoretical assumptions about how things behave. And we can target it to whatever level of excitation we want, because what we're seeing is that as the earthquake gets bigger, the demands are going to get bigger, which then leads to the question of how large should you target. So if you don't consider those higher mode effects at all, if you just design based on the pushover, you have the gray line here. If you design for 3 times your design spectrum, you have the black line. If you design for, say, blue here would be 1.5 times design, so this would be MCE in Canada, or in the US, which is a lot of what's been recommended or assumed by researchers. And there's a pretty big difference in terms of the design forces on the elements of your frame. And so we've looked at modeling that and seeing what it means in terms of collapse. So first off, you can have a collapse due to overturning of the frame. Here we go. So that's what's shown on the left here. Eventually, we start fracturing the post-tensioning, and that will lead to overturning of the frame. This is if we don't model the yielding and buckling of elements. So we'll see this going. This isn't a huge earthquake, but kind of the philosophy that's motivating this is what would be the code minimum for this sort of system? If we wanted it to behave at least as well as anything else, what do we need as a minimum? So to prevent collapse, we model that sort of thing. We also model what happens if there's buckling and yielding of frame elements. So in this case, we'll see buckling of that column under a slightly different earthquake. But again, we're looking at modeling what happens in that case. So it depends on how you've designed things. If you really over-design your frame, then it's going to fail by overturning. If you really under-design your frame, then it'll fail by elements buckling and yielding. And ideally, we would calibrate both so that it's not going to fail under a reasonably defined earthquake. And that's what's shown here. If you don't design for the higher mode effects at all, at least for a fairly aggressive design of the base rocking joint, it's really catastrophic. So it's really critical that you're designing this. We're finding that it's collapsing in most of the MCE level analyses we run if you don't consider the higher mode effects. But even considering at the design level, we're able to get under the limit that's set in FEMA P695. Finally, on the higher mode effects, all of this is assuming that you just have a rocking joint at the base. But some of the thinking during my PhD was if you can control that rocking at the bottom by having, or the moment at the bottom by having rocking, why limit yourself to one location? Why not have, say, rocking at a second location, where you should limit the moment there, and then you would expect that to help control the moment between those locations, and you would expect that because the shear force diagram is the slope of the bending moment diagram, you would get some control over your shear forces. Or, if you put a fancy brace in here that can still be self-centering, but that can cut off the higher mode shear forces, that should help to control your moments. And so we took the same experimental setup I showed you before. It was built as two frames, one on top of the other, so we could clamp them together, and that's the first video I showed you. Or we could release that clamping. We could replace the brace at the bottom with one of these fancy self-centering ones, and we could look at, for the same frame, under exactly the same earthquake, how does the response compare? And here's a video of the same earthquake, but in this case it's allowed, I lost my laser pointer. In this case, it's allowed to rock at this upper joint. You won't see it in the video because it's very fast and it opens about 5 millimeters. But you will see the motion of this brace, which is a self-centering energy dissipative brace. So unless your eyes and memory are better than mine, you won't be able to compare that directly. So let me do that for you. This is from the first video I showed you. This is from the second one. The area grayed out is the area outside the envelopes of displacement, shear, and moment. Shears and moments are calculated based on the accelerations of the floor masses. So you see the displacements in this case are almost the same. They're a little bit bigger in the second video, but maybe 10% bigger. The shears are roughly half of what they were in this case. The moments above the base are much more controlled. And if I animate it, again, this is not a computer simulation. This is what we measured in the lab. You'll see that the displacements are quite lined up between the two. It's driven by the first mode of response. But those shears and moments are cut off by having multiple mechanisms in the system, which is like what we have in most codified steel systems, at least, where if you develop higher mode forces, something yields somewhere else. But not the case with a rocking system with rocking only at the bottom. So those are some issues related to the capacity design of the frame. Moving a little bit more quickly on the connections to the floor diaphragms. I talked earlier about this idea of coupled versus decoupled. And if it's coupled, the connections may not need to be so fancy. If it's decoupled, then we need something that can transfer the horizontal forces without lifting the slab up along with it. So in Forte Health, what they did for this is they have this tongue that's coming out of the collector beam, and that fits inside a slot so that when it's trying to transfer the load, the frame can lift up without engaging that floor slab, which seems like a reasonable solution. 141 Cambridge Terrace, they used a similar detail, and they also provide a pin in a slot so that there's essentially a backup system if either of the two doesn't work the way that it's intended to. This is what it looked like, or another picture of it in practice. And there have been a number of options that have been suggested in the literature. Not many of them have been tested, so this is something we've done at Mac over the last few years. These are the three that we tested at McMaster. So there's a bearing plate type system where we have a rounded plate on a solid one. We tested a pin in a slot, and we also looked at a wide flange connection. So here we're going to yield essentially the plate so that there's relatively little resistance to uplift, and looking at how these perform. It's a 60% scale model, and I'll show a time lapse of this testing. So it wasn't dynamic, it was static. The way this is working is this gray beam is simulating your collector beam, so load is being applied to it by an actuator over here, and then that transfer mechanism is hidden in behind here. And it's transferring very large horizontal loads, up to about 1,000 kilonewtons, into the yellow frame, and we're controlling essentially this red beam with the actuators acting down on it is simulating the post-tensioning, energy dissipation, all of those things that are controlling the resistance of the system, so that we can see at a fairly complicated combination of displacements and forces how that load is being transferred. And here's what it looked like for the bearing plate system. You see it's not that far off, actually, from a flag-shaped hysteresis, which is not necessarily bad, although there's no energy dissipation in the system that we were testing. So this is coming entirely from the friction at that connection. Often the way these have been designed is assuming that you can transfer the load and that'll be like a perfect slider where there's no energy dissipation. So you might look at this and say, this is a good thing. I have energy dissipation I didn't count on, so I'll have less displacement than I expected, and that would be good. You could also look at it as I have larger forces than I expected I would have, and that might be a concern for capacity design. And so my view tends to be, this is not insignificant. We should probably be accounting for it in design if we expect it to be there. We got a similar performance if we put the pin in a slot, but we were able to get rid of that if we wanted to. So we could get something that looks very, very little energy dissipation. And the way of doing that was by having the pin only on one side and only on the side that was pulling. So that the idea is, where's a good example of this? If I have a rocking system, if I'm applying my load and compression here, then I have lots of sliding there and lots of energy dissipated. If I put it on this side, where it's pulling on it, I don't have very much displacement, and since force times displacement is the energy, I'm not going to dissipate much energy. So from a capacity design perspective, this might be preferable, although it's dissipating less energy. But it's trying to get our buildings to behave in a way that's consistent with the models, either by changing our models or by changing the buildings. Finally, that wide-flange stub had the least desirable performance overall. It probably feels more comfortable because you have a full mechanical connection in there, but it fractured at about 2% drift, which if you control your displacements there is maybe okay, but it's kind of on the low end, and a less repeatable response than what we saw with some of the others, at least in the short term. Finally, on the controlled rocking system, non-structural components are something that I think we need to be thinking about. So there's not much value in having wonderful, seismically isolated, top-of-the-line non-structural components in a building that needs to be demolished after after an earthquake. But by the same token, if you have a wonderful structural system and everything in the building gets trashed by the earthquake, your client will probably not be terribly satisfied with that either. So we've been trying to quantify these demands a little bit better. With two key questions about this. One of them is, will that change in stiffness from low to high at a velocity cause acceleration-related damage? So this is based on some theoretical stuff that would show that if you go from a low stiffness to a high stiffness at velocity, we expect an acceleration spike. And notice that this occurs only in a system with a flag-shaped type hysteresis. With a more full elastoplastic hysteresis, you're always softening. You're always going from high stiffness to low, except when you change direction, and then your velocity is 0. So it's something that's unique to the system that might be a concern. So that's how I thought about it, and then it was put much more memorably by some people at the University of Canterbury, where they say if you're on a motorbike and you have very little resistance to your motion, and then all of a sudden there's a spike in stiffness, you will expect a large acceleration due to that. So this is the image that's in my mind, and I'm sure it'll be in your minds now too. And this would be scary. At the same time, from the shake table test that we did, we looked for this sort of thing. We put accelerometers all over the place, and we found, yes, you can measure an acceleration right beside the place of impact, but by the time you get to the floor diaphragms, we weren't able to pick up on any acceleration spikes related to this impact. So we wanted to re-examine this and see, were we missing something? It wasn't obvious in the results, but maybe in the floor spectra it would show up. The other question is these higher mode effects that I've been talking about. If they're driving the forces, well, forces mass times acceleration, there could be some big accelerations that go along with that as well. So this is one of the examples. We've done this for a number of examples now, but this is one from a particular conference paper where we compare a buckling restrained braced frame and a controlled rocking braced frame. They're not in the same building. They're just shown in the same figure here for a place in California. And essentially what we did was we designed both with R of 8, and then we tuned the designs to have the displacements be comparable. So we can look at acceleration demands from the perspective of the same displacement demands. And what that meant was the controlled rocking system, we could allow it to rock a little bit earlier because it's quite stiff. The buckling restrained braced frame, we needed to stiffen it up in order to get our displacements to be the same, which we set at 1.5%, saying we probably want lower displacements in a high performance system. So in terms of drifts, the two are comparable. The residual drifts for the rocking system are essentially 0. For the buckling restrained braced frame, They're not zero. They're not huge. I usually like to use a buckling restrained braced frame as my poster child for bad residual drifts. But at a design level event, we're finding we're under 0.5% in most cases, which means we could probably fix it. But still some preference from a structural perspective for the self-centering system. When we look at floor spectra, the ground level ones are a little bit different here because in this case we scaled the ground motions a little bit differently. But if I look at the roof spectra, and it's similar at other levels, while at relatively long for non-structural components, at relatively long periods, the floor spectra are higher for the buckling restrained system. Sorry, I should say, for those of you who aren't familiar with floor spectra, it's like a response spectrum for the ground. It's just using your floor input as the input instead of the ground motion. In blue is the controlled rocking system, and we get this really peaky floor spectra, where around the second and third periods, we get very large acceleration peaks. I don't know yet how significant that is in terms of damage, but it is a potential cause for concern that we do see these higher mode influenced peaks in the floor response spectra. And those short periods tend to be relevant for a lot of our attached non-structural components, sprinkler systems, for example. In terms of impact issues, we couldn't find any evidence that this was going to actually be an issue. So if you look at floor accelerations at different levels, each of these vertical lines is a moment of impact. This is an attached component with a relatively short period, a longer period. We can't see any spikes in the performance anywhere there. So while intuitively it feels like you're going to have big problems with the impact, both experimentally from the experiments I've been a part of and numerically, we haven't actually been able to see this demonstrated. So those are some thoughts on the non-structural components. Just to wrap things up before taking questions, a couple of words on not controlled rocking systems that are also things that I've been looking at recently. Let's skip through that. I'm looking at rocking with other materials as well. Most of what I've said today is completely independent of the fact that it's steel. The rocking is what's controlling the response, not the material. And so we're looking at rocking wood, we're looking at rocking masonry. In those cases, there are detailing issues to think about. There are considerations in terms of what combinations of post-tensioning and energy dissipation might be attractive. But conceptually, from the mechanics of the system, it's quite similar. So those are tests. These ones just finished up. We haven't processed the results yet. These we will be testing later this year. We've been looking at replaceable brace modules. So this is an idea of if you're designing a concentrically braced frame, which is going to be damaged in a design level earthquake, why don't we design in a way where we plan for how we will fix it after that earthquake? And so some concerns that we've had with the way we conventionally detail these. One is that usually your gusset plate will promote out of plane buckling of the braces, which means if it's on the exterior of your building, you've got a 50-50 shot that it's going in the direction of pushing the cladding off your building while everyone is evacuating, which is a potential life safety concern. In North American practice, at least, we're usually using field welding for these, and we tend to prefer bolting on site and welding just in the shop. And relatively difficult to replace in the event of an earthquake because your damage is not just to the brace, it's to the gusset plate, which is welded into place, and so somehow you've got to cut that out, weld a new one in. It's doable, but it's perhaps not as simple as it might be. So we've developed the idea of a replaceable brace module where we try to constrain all of our damage into a module that's bolted into place. So this stiffener plate is welded in the shop onto a beam, and we have a brace that's bolted into there. It promotes buckling in the plane. We try to increase the erection speed because we're bolting on site, and try to make it easier to repair after an earthquake as well. So this will be a time lapse of some testing we did just a few months ago on this system. These are the brace modules. We tested with the braces in there, and then after we had broken the braces, we would take them out, put new ones in, and repeat the test to see that we got essentially the same performance, and then push it even further to see how much reserve we got with different kinds of beam column connections in the system. And overall, we're finding that the system is behaving the way that we would expect a more typical system to, but it's buckling in plane, and we're limiting our damage to the part that we're unbolting. Finally, this topic has been interesting me over the last couple of years. I talked about structural design, I've talked about some of the non-structural, putting them together. Because overall, I think what the public is interested in is an overall system, and most of the value of our building is not in the structure itself. So performance-based earthquake engineering is pretty well defined at this point, even though there are a ton of assumptions that go into it. So it's going through a number of steps. But what we've been looking at is if you upgrade your non-structural components, there's a cost associated with that, and you expect a payoff in terms of savings in annualized losses due to earthquakes. In addition, if you change your structural design, that will also have an influence on the demands of the non-structural components, and that also will affect your overall losses. So we've been taking the idea with a set of potential structural designs, wrapping it in a genetic algorithm to optimize and try to see what overall is providing our best things. Essentially, if you're a client and you're trying to decide where am I going to spend my money? Do I spend it on upgrading the structural system? Am I better off spending it on the non-structural components? Do I do some sort of a mix? Looking at that. And so for one of the case studies, at least, this is a three-story building with pre-Northridge connections. Of the cases that we looked at, putting viscous dampers in there was working out great. It was the best option and worth doing, even if that reduced the amount of money available for non-structural savings, because you will help to control both displacements and accelerations in the system. In terms of non-structural upgrades, there's a bunch of different things you can look at. From an economic perspective, the mechanical equipment is often worth upgrading, especially the chiller. That one was one that tends to be relatively cheap and easy to upgrade, and relatively high losses in the event of an earthquake. So that's something we're playing around with and seeing what it means for different systems. Just before taking questions, I'd like to acknowledge a number of people. Most of the work I've presented here has been done by a large group of grad students over the last number of years. My PhD supervisors for the work I presented there, various lab staff, and then people who have shown me around New Zealand and taught me some things here. Finally, thank you for taking the time to be here. I hope you'll have some interesting questions for me at this point. Thank you.
Thank you, Lydell. Very interesting presentation. Very topical. Let's take some questions then.
Yes, please.
You showed that example there was that New Zealand example with the floors decoupled.
Okay. Yeah.
And then the other one with the floors not decoupled.
Yeah.
Do you get any damping or issues from the floors being coupled? To take account of that?
Any damping issues? So.
Sorry, energy dissipation.
Yeah. So just so that it's on the recording, the question had to do with energy dissipation you might get within the decoupled system in this case. What we found from the lab tests is that energy dissipation is non-negligible, which you could think of as a good thing. I think most of the time it has been non-modeled, and so taken as a positive, but it could also increase your capacity design forces.
So is that hard to model on the left-hand side?
In this case, so most of the researchers, and as far as I can tell, designers, have tended to assume that this one is easy to model because it's negligible. And what we're finding is it's not negligible. And so there's been a tendency to avoid this system because it seems like it's harder to model. But I'm not sure that it's actually harder to model. It just feels like it's going to be harder to model. And so where a decade ago I hadn't done the lab tests yet. And so at that point, I was totally not sold on the system. I was at that point in my PhD. Those of you who have done graduate degrees know this experience. The trough in your PhD where you feel like the system you're studying is a bad idea and you're wasting your time looking at it. Then I did the lab testing, and it convinced me that it could actually be a good idea. By the end of that, I was thinking this is the way to go because I was really worried about the impact problems and some of the challenges in modeling this accurately. At this point, I'm more swinging the pendulum in this direction. I think this is going to be easier to build, and I think we will be able to account for some of the modeling challenges. I'm not sure we're all the way there yet, at least in ways that I would feel confident in. But I think 5 or 10 years from now, this will be the way that I would tend to go. Because this one involves quite a bit of special detailing. This can look a lot like a concentrically braced frame without anchor rods. And I think that sort of thing becomes a lot more feasible. I'm not sure you need post-tensioning either, is another piece of it. Yeah?
While we're on the decoupled systems, so the decoupled system relies on your post-tensioning essentially providing post-tensioning. In the real-life situation, how do you make sure that that post-tensioning actually stays in place and doesn't uplift or move during the action?
Yeah.
Obviously in the lab it's the strong flow, but in real life, what is holding it?
Yeah, so again, just so that it's on the recording here, the question had to do with what gives us confidence that when you have this post-tensioning, which is so critical to the system, that in an actual application, it's not going to go somewhere else, that it will be stable in there. I would say the same things that give us confidence with any post-tension system, that it will stay there, which involves some detailing considerations for sure. And it's something you would need to be thoughtful about, but I think there's a long history of using post-tensioning within structures that seems to work as far as I can tell.
What is it fixed to?
What is
What is it fixed to?
what's it fixed to? The foundation. And so in some way, you'll need to provide an anchorage detail that can do that. There's a number of different ways that's been done, often with some strut and tie modeling to figure out then where those forces are going. But if you embed it far enough into the foundation, I haven't looked at that detailed aspect of how it's been done in practice, but I know that they've built these systems with the post-tensioning and assume that that's something that since they've built it, they must have figured out a way. Maybe that's not a good assumption to make, but these systems tend to be pretty heavily peer-reviewed, and so I would expect that would have been considered. But yes, that would be an important thing that you would need to consider. Thank you. Yeah, Pierre.
Have you seen any floor damage prevention details on the coupled?
On this sort of system?
Yeah.
So Rick Henry was involved in some tests at ILE recently. There it was a concrete system, but so your floor system might look different there. But what they're finding is that you can accommodate this uplift with a controllable level of damage within the floor system overall. So in this particular case, they put some slots in some of the bolted connections to try to allow the rotation between, as that frame is uplifting, and the relative rotation with the beam. There are slab details, again, referring to the stuff that was done, that was tested at ILE. So yeah, those are some of the ones that have been done. It's something where, again, I think the research started here, and the practice was split between the two. And so I think there's still value in having more testing of this kind of detailing. But it seems like it is something that would be achievable.
The moment we say it's coupled, we assume that the weight of the floor, the gravity system, is then channeled to that brace frame.
Mm-hmm.
If we have any other detail that's trying to decrease the potential damage, then the effectiveness of the weight transfer is then decreased.
Yes, you're exactly right. So you can't have it both ways. You can't have your cake and eat it too. You either get the beneficial effects of the weight in helping to clamp things down, along with the potential downside of slab damage, or and impact problems, or you avoid those potential problems, but you don't get the weight. There's no way of having one without the other. And so then it becomes a question of, is your detail doing what you expect it to do? There was a presentation I heard once that really sticks with me, of the idea that as structural engineers, we're trying to get our buildings and our models to behave in the same way. So we can improve our models to match the buildings. We can change the buildings to match what we're modeling, but they do need to be consistent with each other. Yeah?
So maybe I'm wrong, but during your presentation, I felt that you don't feel comfortable using direct displacement approach with this system. So am I wrong, or?
I'm not sure I would go quite that far of saying I don't feel comfortable with it. It's not the direction that I have gone with it, because embedded in a direct displacement approach is the assumption that the secant stiffness is a good parameter for quantifying the demands on the system. And from what I can tell, it seems that secondary stiffness, and therefore the secant stiffness, is relatively insignificant. Now, if you calibrate the approach correctly, I think you can design the system with any approach. But the way that I have tended to prefer to look at it has been from something more consistent with more traditional force-based design, with a very critical check on your displacements, because that displacement check is what's going to drive the entire design, not unlike a moment frame, at least in North American practice, where you have a value of R in there, but you never actually use that value. It just gives you an initial design, and then your displacements control it. I would think of it as being analogous to that. So I know that some of these have been designed with direct displacement-based design approaches. I'm not sure that you can't do that. My preference would be for something more like traditional force-based.
And my second question, just quickly, the projects the damping ratio roughly you were getting from your rock?
I don't know off the top of my head. Sorry. Yeah, I'm not sure. It would be not zero, but I don't know how close to a full elastoplastic, or to a full, the maximum you can get while self-centering. I would guess, but I haven't verified this. A lot of the time people assume the more energy dissipation the better, which is true for controlling displacements. And so we'll try to maximize it. And so that would, if I were guessing, that's what I would guess. But again, I don't know. And I don't think that's a bad approach. I think usually you would want to maximize the energy dissipation. I think there are some cases where you might not be able to provide it, and you can have a stable system even without any energy dissipation. And you get the most bang for your buck on the first bit of energy dissipation that you put in there. Yeah. Ken, I saw your hand up. Oh, sorry, I heard something here too. Yeah.
Also, based on what you say, we don't need to do nonlinear time history analysis and those sorts of stuff, just response spectrum analysis.
So my feeling is that it would be, I should be getting in the habit of saying, so the question was, am I saying that we don't need nonlinear time history analysis for the systems? I think we can at least get to that point. I would feel comfortable designing it that way. I'm not sure I would feel comfortable saying everyone can do that without some fairly well described steps towards doing that. But the avenue that I've taken in my research over the last number of years has been to say, what are the steps that we need to codify something like that? And critical to that in my mind, in the developmental, in a lot of these self-centering systems, the idea has been this is a Cadillac system. It can do whatever we want it to do. And so let's make it invincible. It's going to be able to withstand any earthquake with zero damage. And it's great to do that. But I think that if we look at codifying something, I don't think we need to expect higher performance of this system than we expect of anything else. I think that if we want to put it in a code, we should expect the same minimum level of performance as everything else. And if that minimum level of performance is no good, which I think is quite possibly the case, that we should increase that performance expectation for every system that's out there. And so for some of these things like, can you design it without nonlinear time history analysis? I think that if your stiffness in the secondary, like while it's rocking, if you have something to ensure that it doesn't go negative, that you've got something to overcome your P delta effects, and if you provide some level of energy dissipation, I think we could set a set of code provisions that would allow you to design it reliably without that. Assuming, as we assume with everything in the code, but this might be a more hazardous assumption in this case, assuming that the engineer knows what they're doing and doesn't make a mistake. Because there is a potential danger in this case of if you mess up your capacity design, the whole system goes wrong, as with every system, but this isn't a system that you learned in undergrad.
And another one, the engineers here should deliver the concept quite early, so is there any rule of thumb or something to size something and give it to the client and later on come back and define it?
So the question was about rules of thumb for sizing things. No, so the short answer to that is no. You can get a feel for things as you've worked with them. The initial calculations are not that hard, so it depends on the situation that you're looking at, but figuring out what the rocking system is going to do, that would be relatively easy to do on the back of an envelope. It's a free body diagram. You have weight, you have post-tensioning, you have energy dissipation, you have geometry. And that can tell you everything that you need to get a pretty good estimate of the flag-shaped hysteresis, which can give you a pretty good estimate of the displacements that you would expect. So for the design of the rocking joint, I think that one you can do pretty easily on the back of an envelope. In terms of the capacity design of everything else, that's something that is probably a bit more involved. And we have simplified approaches to it, but that's not a back of an envelope sort of thing. So it depends then on what you're designing. I think I can think of retrofit applications that I've seen where it hasn't been done, but where I look at it and say, I'll just let the system rock because you have so much strength there. But if you clamp it down at the bottom, then you're going to start trying to use that strength. And if you have like unreinforced masonry, you're going to start breaking that apart. If you allow it to rock and control the rocking, you'll have plenty of capacity there and just allow the rocking. But for a new build sort of thing, I'm not aware of good rules of thumb for the whole package. Yeah?
If you are the designer, and based on your results, research results, would you go and select the coupled system to ensure that proper load path transfer from the slab, concrete slab into the bracing system?
Honestly, at this point, I would lean towards the coupled one. I would lean towards this one. Here you're relying on a special connection detail, and we've tested some and they seem robust, but here it's more conventional. You're just relying on the slab being able to withstand some uplift. Yeah, so I would go this way, if it were me. I would go with the coupled. No, I don't think that this is a bad solution. I think that this is likely to be a more difficult to build solution. And so I am inclined increasingly in this direction. And what's changed for me over the last decade thinking about this, I was really concerned 5 or 10 years ago about the floor damage that would be in there. But what we're seeing from some of the tests is that as long as your bay lengths are not super short, that you should be able to handle the damage that might come to the floors. That the amount of uplift spread out over the length of a bay is not actually all that huge. The slabs have the flexibility to accommodate it. The impact problems, there's a student at École Polytechnique working on this who made a couple of key observations in my mind. One was when we design our columns, we're designing for gravity loads which have load factors on the dead and the live loads. During the earthquake, you are expecting unfactored dead and live loads. So you have some factor of safety built into that column already that can accommodate some level of impact problems. The other thing that he's pointed out is that we drive piles. We put very large forces on steel columns, essentially, and they generally don't buckle. So we are able, in some way, to handle very short bursts of very large forces without instability of the system. So I think there's room to be explored on how to quantify that, and I'm not sure that we're all the way there yet. But where 5 or 10 years ago, I would have thought this is the way to go. At this point, I think this will be easier to do, and I think we will be able to handle the performance issues that might come up. Thank you.
Shall we take one final question?
Yes, you mentioned that application for existing buildings. How many applications did you have in proportion to new buildings? And also, would you go with the coupled, maybe because it's easier?
They're quite small numbers. The numbers of applications that have been built. I learned today that there's a building here on campus that was retrofitted with a masonry building that was retrofitted by putting unwanted post-tensioning in there and turning it into a rocking system. I understand, so there are a number of new builds that have been done. There are some retrofit applications, but it's not like this is a pervasive system anywhere. And I think it's probably fair to say, someone might correct me on this, but I think it would be more common in New Zealand than anywhere else in the world. At this point, at least. I do think there's a lot of potential here. I think in New Zealand, you're quite good, you're quite quick to adopt a technology that seems promising. And in some cases, that can be really good, and in some cases, it can be kind of scary. But either way, there's less inertia here than there is in many places. Yeah. Like I say, I study the earthquakes from a safe distance. So. Yeah.
Well, now you live in Christchurch.
I felt an earthquake in Turinga yesterday when I was there. Yeah.
Question. In the case of the seismic, the cost perspective, what's the advantage of using this system compression with inline friction dampers or some kind of base isolation system? Because in the engineering side, when we want to design the structure, we want to decide, for example, we want for the bracing, for the friction damper, we have different options.
So the question has to do with the advantages of this system compared to the many other systems that are out there, right? And I think we'll finish on this question as I understand. Yeah. So I think there's no one system that's going to be the answer for everything. I think base isolation can be a wonderful solution in some applications. I think this can be a great solution in some applications. I think that some of the more conventional systems can be great solutions in some applications. But as a researcher, it's trying to develop the systems that then you as practitioners can implement in the cases where they are viable. So I don't think this is ever going to be used for all of the buildings that get built. But I think there are cases where the structure wants to rock anyway, and you might as well try to harness that and control it rather than fighting against it.
Good. So please join me in thanking Lydell.
Thank you. Thanks very much.